let me return to my first question. Suppose you have a convection equation, du dt plus du dx equals 0. So you have a structure which moves from left to right. So this would be a non-separable structure. So the POD, you need a horrible number of time modes, you need a horrible number of space modes, because everything is locally localized, but there is a structure described by this convection equation. You can also say it's a realization of the Taylor frozen flow hypothesis or something like that. Now there are a couple of approaches, convective POD and so on. My question is, by how much can you change your general ABC matrix decomposition in order to get this convection? And to make this a bit more difficult, let's assume we have a flow where we have several convection velocities depending on in which region we are. For instance, we have a mixing layer, then there's a high-speed stream, a low-speed stream, and maybe you have 3 characteristic convection velocities, and you would like to catch these spatio-temporal modes to 3 convection velocities in the most energy or residual minimizing way.
Do you also have an easy question, or? I don't know. I mean,
these algorithms exist, but it's based a bit on a cooking, so it's a bit on a recursive construction side. So first you take one convection velocity, you decompose something, now you look at the residual, you decompose something.
But what I will do is something like convective. If I know that something is just moving, I will expect some sort of
single vortex. Let's say for the UDT, let's say it's always a bump, 0, 1, and something like a square, which moves left to right, let's say from 0 to 10.
I will try to get the convection velocity, then shift all my snapshots such that they all fall in the same thing. Now the thing is not shifting anymore, and I do this. Then I reshift it back, and I skip the problem.
But you have to conclude. You have to work with space-time mode to start with,
yeah.
because otherwise your shift will always create a gap in your field. If you shift something from left to right, you will have some things on the left side which is undetermined. These algorithms exist, so these are convective POD algorithms. But I wonder in how far, if in principle the ABC method could be used to do this, or if you have to rely on some recursive algorithm to resolve the coherent structures.
I will reply with a question, because I'm not sure. Is it possible to simulate a shift via a simple matrix multiplication? The answer is, I think, yes.
Yes, but you have to introduce some new results for what you have shifted.
Yeah. Or you have to say that what is leaves comes back.
Yes, but normally the flow does not have the property.
Yeah.
Cylinder wake, for instance.
Yeah, well, you will have some missing data. I don't know the answer. I don't know how to deal with that. I need to think about this. But somehow, if you try to reproduce this shifting through a matrix multiplication, let's say that this matrix multiplication acts on the left, so on your spatial structures, then I will expect that this matrix multiplication is acting on the phi's, so on the A's of this matrix. Factorization.
It's a bit like a companion matrix.
Yes, but for space.
For space, yes.
Exactly. That's what will come to mind. As long as you can reproduce whatever operation linearly through matrix multiplication, if your linear operation is happening on the columns, so it's going to hit on the spatial structures. If it's happening on the rows, then it's going to hit on the temporal structures. As long as you can do it through matrix multiplication, I think the framework holds. In the moment you cannot, then you have to do something else.
Thanks.
We have one from very far.
Thanks again. I wanted to ask a question about because I feel like there's so many of these decomposition methods which are coming out now, which are basically like some kind of temporally filtered POD method.
Sorry, I'm not sure.
Oh, sorry. I feel like there's many different kinds of these temporally or frequency filtered POD methods which are coming out, and sometimes I write papers and then I try to publish them just using POD, and people say, why didn't you use spectral POD? Why didn't you use blah 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 blah? And I kind of thought about this for a while, and I said, okay, in a very complex flow, okay, in something like I work in combustion chambers, you have a swirling flow, you have sometimes some cooling flow features, you have very complex physics going on. And my question to you is why do you think that limiting the dynamics of a structure to just one frequency or one band of frequencies is relevant for a complex flow?
That's a very deep question. So first of all, a comment. If someone asks you, why didn't you use this decomposition, question mark, without saying, maybe because you know, every decomposition aims at answering some question. I mean, you want to look at the data in such a way that you see what you want to see on that. A bit like Mars in the lecture of Javier Jimenez, if you want. But every tool has to be tuned for what you're looking for. So if you are looking for a particular thing, for example, let's say the case of the cylinder, and I ask you, I'm interested in knowing what is the temporal structure of what is happening before the first transitory. You cannot do that with POD, and you cannot do that with DFT because your frequency is changing, okay? So suppose that you do that using another thing, and I ask you, why didn't you try with POD? That would be, you see what I mean? I mean, every decomposition is tuned for a specific question. That is the first part of the answer. The second part is, why do you like to see only special frequencies? I think one big point was also raised by Professor Noack in his review, the article when you review the SPOD by Sieber, is because frequencies are easy to interpret, I would say. If I tell you, you know, the turbulence cascading, you like to describe this in terms of frequencies and scale. Intuitively, you think in terms of frequency. You say this scale interacts with this one, but not really with this one, okay? So in the case of the jet, for example, you wouldn't expect to see 1 Hertz in the potential core in the Kelvin Helmholtz where things are going very fast. Understand what I mean? And you will not expect to have 300 Hertz on a wall flow that is going at 1 meter per second. I mean,
yeah, but I mean, for like taking your example of a jet, for instance, you have Kelvin Helmholtz instability, you have some high frequency structures, and then they somehow combine with each other to then form larger structures or break apart to become smaller structures, and you get harmonics and subharmonics. And I'm not entirely convinced that there isn't some value in that POD which you show there, because actually maybe what it's telling you is, yes, the large structure is stronger downstream, but actually it has some link to something which happens somewhere else in the flow, because there is a convection, there is actually information which is traveling from where your jet is coming out to the end of your domain.
Sure, yeah, it is a bit the question that Professor Noack is asking. I mean, the mPOD or this factorization cannot tell you that if you have that frequency there, maybe you will have another one somewhere else. You see? This kind of causality cannot be, I think you cannot ask for that to a decomposition. A decomposition takes data and you represent it in some way. Now, what you can do, maybe you can construct some reduced model, and let's see, for example, how this structure should evolve according to your equation, and then we enter into another domain. But if you are just looking at analysis, I will not ask, I mean, it's very difficult to say, okay, what happened here actually later is here. You see, in this convection-free ways of factorizing the matrices, I don't think you can see it. But maybe I need to think more about that. I don't know. I don't know if I answered to
No, I think you did answer the question, basically. I think it really, I mean, I totally agree with the point about each decomposition method is important for what you're interested in looking at.
Yeah.
And I think if you understand where structures are coming from or the physics of how things lead from one thing to another, then you have a model in your mind, then you can think of a decomposition method which is giving you the answer that you want.
Yeah.
But if you don't know what you're looking at, then you don't necessarily know how to ask the question. But I guess the point from my perspective is that in an ideal world where we can imagine a decomposition method, which is actually answering that golden question of what thing leads to what thing and how are these things connected, I actually prefer a method which does as little, assumes as little as possible in the analysis.
Sure.
And that's why, I mean, it's just a little frustration of mine when I get back reviews, and
I share this frustration. And you have summarized my answer much better than the one that I gave you. So thank you, because the way you summarized my answer is much better. Yeah, I think that this is analysis, let's say, and to answer the kind of questions you're looking for, you need something else. You need modeling. You need to move this to the next step, to put this together with a model, to say something more about what you're looking for. And you need to know what is the question, which is not the easy. I think this is the hardest part sometimes. Huh? You have a lot of data, but you forget what was the question.
A slight aside, which maybe should be taken offline, is the difference
You're
between
recorded, eh?
SPOD and the other SPOD, because there's two SPODs, and
Sure.
we had a description of one and then the other at various times, and I've worked with one and not the other, and it would be useful to have some clarification about what they are, where they come from, and what the differences are, if there's any connection or...
No, there is not. I don't think there is any connection between them. You're talking about the one from Sieber and the one from Tone. So the one from Sieber, as I said, you try to have a spectral purity. So you try to go towards a POD mode that has one frequency. You try to push it towards Fourier. In the other case, what you're doing is something similar, like you know P. Welch. When you want to compute the spectrogram of a signal, which is sufficiently long, you break it into different parts. And then you take an average of the spectra in each window. It's like windowing the transform and then taking the average. The other spectral POD is something like that. So what it's doing is computing the POD in the spectral correlation matrix in KF, the one that I've shown you there as a KF. But if I stop there, I have exactly a POD. Exactly a POD. So instead of doing it on the KF, I do it on a weighted average KF, on a window, on a P. Welch to KF. You understand what I mean? So what you're going to do is you are ensemble averaging your spectra, and the spectra of the POD modes that you will obtain are going to be cleaner, meaning more noise-free, more averaged. If you have a statistically stationary problem, I think this is an excellent tool. Okay, but you're not obliging one mode to have one frequency. You're ensembling, averaging the spectra of possible POD modes. Okay, while in the other, you're trying to move the POD mode to become more like an harmonic. Did I answer?
Yeah, I mean, I think I just need to actually read a paper on the second method, because the Sieber method I understand quite well, but the other one
we can take a coffee, paper, and pen, and I can show.
Thanks.
I try to have a simple question right now. I think your method can also be, so you are separating frequency, and this makes perfect sense because most conceptual methods are based on having idea where certain frequencies should be located. But you could reverse the project. You can say instead of a frequency decomposition, you can make something like a domain decomposition. And let me tell you why it's very relevant. Suppose you have two cylinder wakes, same frequency, and they happen to be in phase, but actually you want to have one expansion for one cylinder wake and another expansion for another cylinder wake, because they're not interacting with each other. And I think your framework can be easily transcribed to solve these type of problems.
Thank you. It's a fantastic idea. I already started, in fact.
I should not be surprised, right?
It's a fantastic point. I mean, so far I've always been focusing on partitioning frequencies in time, but what if you partition frequencies in space, or as you said, localized things? I think there is room to combine this in many things, and this is an excellent suggestion. Excellent. Thank you.
You're welcome.
Thank you. Picture? Who forgot the mobile? Oh, you know. Here it is. Yeah. Okay, thank you then. Let's go for the picture.